So hello everyone, my name is Emna Bouzaiene. I'm a master's student at the National Institute of Scientific Research, and today I will be presenting part of my master project, which focuses on a small-scale experimental study on how mine water can be harnessed for geothermal energy production. So in underground mines, pumping water from underground workings is an essential operation. In active mines, it ensures that underground workings remain accessible and safe when mining occurs below the groundwater level and water inflow takes place. In abandoned mines, pumping helps prevent complete flooding of the galleries and reduces associated risk such as collapses and environmental impacts. This pumped water is often considered as an environmental liability and is simply discharged at the surface. However, it can be a local and renewable energy source for geothermal application due to its relatively stable temperature after circulating at depths for long periods. Underground mines are particularly suitable for geothermal systems applications because of the existing infrastructure and also because there's already a water pumping systems in place which facilitates the integration of heat recovery systems. An innovative approach is therefore to use this pumped water to supply a heat pump and recover its thermal energy. This heat can be then used, for example, to heat nearby buildings, leading to energy savings and reduced greenhouse gas emissions compared to conventional heating systems. Several geothermal systems using mine water from abandoned mines are already operating worldwide. However, in active mines, only a limited number of studies have evaluated the available geothermal resources, and to date, no documented pilot project exists in the scientific literature demonstrating the use of dewatering water for energy purposes in an operating mine. In this context, these projects aim to install and operate the first operational geothermal system using mine water in an active mine in Quebec. The objectives are to assess the feasibility of such a system, to evaluate how it can be technically installed and operated in an active mine, and to estimate the amount of thermal energy that can be produced at the small scales. Also, to evaluate its performance. So the pilot system was installed at the Goldex mine, located 4 kilometers west of Val d'Or in Abitibi. It is an underground gold mine reaching a depth of approximately 1,200 meters. The mine has been in operation since 2008 and is expected to continue into 2030. The system was installed near the sedimentation pond, which receives mine water pumped from underground galleries of Shaft 2. This pond has a total capacity of approximately 12,000 cubic meters and typically contains around 5,500 cubic meters of water under normal operating conditions. The sedimentation pond is divided into two sections, the north and the south basins, which are interconnected. The pilot system is installed right near the South Basin. So this is a simplified representation of the system. It is an open-loop geothermal system, meaning the heat is directly extracted from the mine water. The system consists of two circuits, a primary circuit where mine water circulates, and a secondary circuit containing a mixture of water and antifreeze that carries heat through the system. In our case, the antifreeze used is a 30% propylene glycol. The two circuits are separated by a plate heat exchanger, which allows heat transfer from the mine water without direct contact with the heat pump, preventing corrosion and clogging issues related to water quality. The recovered heat is then upgraded by a heat pump. A heat pump works like a reverse refrigerator. It extracts heat from a relatively cold source and raises it to a higher temperature suitable for heating. The produced heat is then released through an air heater outside of the container. Finally, the cooled mine water is returned to the South Basin. The system is also equipped with several sensors to monitor its operation, including 6 temperature sensors, 3 flow meters, and an electric power consumption meter. All the data is then transmitted to a monitoring system located in a control cabinet. The data are centralized in a backnet server. The system allows real-time visualization of sensor measurements through a graphical interface and also enables automated data acquisitions to be scheduled based on the desired time step. So to give you a clearer picture, here is a short video of the system and its main components. So we got the unit heater, the temperature sensors in blue, and in yellow the flow meters. This is the plate heat exchangers. And this is the circulation pumps to control flow rate and expansion tank to control the pressure. This is the heat pump. That's the power consumption meter. And this is the control cabinet containing the monitoring system. So the system was installed on November 3rd, 2025, followed by a startup and adjustment phase. A first continuous operation test with data acquisition was conducted over 7 days. The system was then shut down to prevent freezing in the external pipes due to cold winter conditions in this region of Quebec. So the temperature and the flow rate data collected over the 7-day period were used to calculate the thermal power in the different circuits of the system. This power mainly depends on the temperature difference between the inlet and outlet of the fluid, as well as the flow rate. These calculations allow us to determine the total thermal energy produced during the test. The system performance is evaluated using the coefficient of performance, the COP. It represents the ratio between the heat produced and the electricity consumed by the heat pump, and the compressor power is then determined from the thermal power produced in the glycol loop and the COP. Unfortunately, due to a malfunction of the electricity meter, the heat pump's power consumption could not be measured directly during this test. As a result, the COP was estimated using the manufacturer's heat pump performance data, and a relationship between the COP and the source side inlet temperature was applied. In our case, this corresponds to the inlet temperature of the propylene glycol entering the heat pump. So here we can see the variation of mine water temperature at the inlet and outlet of the system. The inlet temperature remains very stable, ranging between 10 and 13 degrees Celsius. After heat extraction, the water returned to the basin is between 8 and 10 degrees Celsius, and the temperature difference throughout the whole test remains consistent around 2 degrees Celsius. These results confirm that the mine water is a stable geothermal energy source. The average flow rate used by the system is about 12 GPM, while the load side flow rate remains stable between 9.1 and 10.7 GPM. During the test, we briefly reduced the flow rate to evaluate its effect on the temperature difference. However, this caused the system to start short cycling, so we just fixed the flow rate to 12 GPM throughout the whole test. Here we can see the variation of the thermal power extracted from the mine water and the thermal power delivered by the heat pump during the test. On average, the system extracted about 7.2 kilowatt of heat from the mine water. After passing through the heat pump, the delivered thermal power reaches approximately 9.7 kilowatt. The difference between the extracted and delivered thermal power is approximately 2.4 kilowatt, corresponding to the electrical input of the compressor. The values remain stable throughout the test period, indicating reliable and consistent system operation. The coefficient of performance of the heat pump is approximately 4.1. This means that for each unit of electricity consumed, the system produces about 4 units of heat. This performance level is typical and considered satisfactory for this type of geothermal system, which generally operates with COP values between 3 and 5. Water pumped from the underground galleries is cyclical. When pumping occurs, the average flow rate is 1,143 GPM, which corresponds to about 255.7 cubic meters per hour. During the 7-day test, the average pumped flow rate was 476 GPM. In comparison, our pilot system uses only 12.5 GPM, which represents approximately 2.6% of the average flow rate pumped from the underground galleries. So as shown earlier, using 2.6% of the total flow rate allows us to produce an average thermal power of 9.7 kilowatts, and an extrapolation was performed assuming that the temperature difference between inlet and outlet mine water remains constant at around 2 degrees Celsius in order to estimate the potential thermal energy that could be delivered. So based on this assumption, if 50% of the flow were used, the system could produce approximately 186 kilowatt on average, and ultimately using 100% of the flow would result in a thermal output of about 374 kilowatt. In conclusion, an open-loop geothermal system using mine water was successfully installed and operating in an active mine site. The system operated continuously and in a stable manner over a 7-day period. A total of 1,217 kilowatt-hour of thermal energy was extracted from the mine water, resulting in 1,626 kilowatt-hour of total useful heating energy produced. Another extrapolation was performed, assuming that the system operates stably over an entire year using 2.6% of the average flow rate pumped from the underground galleries. Under these conditions, the system would produce approximately 84,000 kilowatt-hour per year. To put this into perspective, the average annual heating demand of a single-family house in Quebec is about 22,000 kilowatt-hour per year. This means that the system could theoretically cover the heating needs of about 4 single-family houses. If 50% of the pumped mine water were used, the system would produce 1,615,000 kilowatt-hour per year, which could supply the heating needs of about 73 single-family houses. And finally, if 100% of the pumped flow were utilized, 3,230,000 kilowatt-hour per year, corresponding to the heating demand of about 147 single-family houses. We then evaluated the environmental and economic benefits of such a system, assuming that the system operates over 1 year with constant flow and temperature difference between inlet and outlet. The heat pump would emit approximately 0.21 tons of carbon dioxide. In comparison, if the same amount of energy were provided by a conventional heating system, for example, a natural gas boiler, it will emit 15.12 tons of carbon dioxide. This means that the geothermal system can reduce CO2 emissions by 98.6%. And from an economic perspective, the pilot system would have an electricity cost of approximately 799 Canadian dollars. In contrast, providing the same amount of energy with a natural gas boiler would cost 1,802 Canadian dollars. This corresponds to an energy cost reduction of approximately 55.7% using the geothermal system. So the next steps of the project include restarting the system in late April to early May 2026. In fact, the startup phase has already begun 2 days ago. Another priority is to resolve the technical issues encountered during the first test, such as rewiring the electricity consumption meter and also enabling remote access for system monitoring. A further objective is to operate the system continuously from May until November 2026. And we are also considering the possibility of operating the system in cooling mode during the summer. And finally, the goal is to collect sufficient data to fully assess the energy, economic, and environmental potential of heat recovery from mine water. Thank you.